Okay, so on Tuesday, we were able to look at a simple spring element made of two nodes, node 1 and node 2. And we said that there are element forces F1 and F2. Node 1 and node 2 have the displacements U1 and U2. We derived the element stiffness equations for a spring or bar element. I said this is the simplest element that we can use in the finite element method. And we wrote this element stiffness equation as F1, F2 equals to K1 minus K1, minus K1 and K1 multiplied by U1 times U2. We call this matrix, the square matrix, we called it the stiffness matrix, the stiffness matrix. Next, we said if I can write all the element stiffness matrices for a system, we can use these element stiffness matrices to assemble the global stiffness matrix to write the global stiffness equations. And we took an example of two springs that are attached together at node 2. So these two springs, spring 1 extends between node 1 and node 2, and spring 2 between node 2 and node 3. So node 2 is the shared node. Spring 1 has a spring stiffness K1, and spring 2 has a spring stiffness K2. I can write the element stiffness matrices for spring 1 and for spring 2, or element 1 and element 2. So for element 1, it's going to be the exact same matrix here. For element 2 or spring 2, I'm going to replace the K1 with the K2. But it is important to understand where each entry within the stiffness matrix relates to which degree of freedom. So looking at element 1, it extends between node 1 and node 2. And therefore, degree of freedom 1 and degree of freedom 2, or rather U1 and U2. So if I'm referring to this as degree of freedom 1, degree of freedom 2, I can label my matrix 1 and 2, 1 and 2. While looking at element 2, it extends between 2 and 3. So I can mark where these entries relate to degrees of freedom 2 and 3 and 2 and 3. Now, I showed you on Tuesday that we are going to use this numbering scheme and the method of superposition to assemble the global stiffness matrix. The global stiffness matrix is here. And basically, I mark my global stiffness matrix. I expect to see a 3 by 3 corresponding to the external forces and the global displacements. So now I have this total 3 degrees of freedom. So I expect to have a 3 by 3 matrix. This 3 by 3 matrix is going to be comprised of stiffness matrix of element 1 superimposed on the stiffness matrix of element 2. Each is going to go to its corresponding degree of freedom. So the stiffness matrix K1 will go between 1 and 2, between 1 and 2. Here it comes in blue. And then the stiffness matrix K2 would come between 2 and 3. Here it comes in black. So you will notice that the shared entry is that of row 2 and column 2, where I'm getting contribution, this K1 and also this K2. Is that clear? So this here is a K1 plus K2. There is a blue and a black, because this is the shared nodes. And we have 2 zeros. You will notice that the stiffness matrix is always a square matrix, is symmetric about the diagonal. So if you look at the diagonal, I have here minus K1, minus K1, 0 and 0, minus K2, minus K2. And the diagonal entries are always going to be positive. So these are some of the characteristics of the stiffness matrix. Once I put together my global stiffness matrix, I can use the global stiffness equations and apply the boundary conditions to solve for the unknowns. Once we solve for the unknowns, this could be displacements and could be external forces. I can use all the known displacements now and go back to my element stiffness equations to solve for element forces. Today, I would like to work out an example to demonstrate how to apply the finite element method. So let me first start by trying to put together the steps that we're going to take to complete the finite element method process. I would say number one is meshing or discretization. So develop the mesh by identifying elements and nodes, making sure you are using adequate elements. And we learned about different types of elements, as in beams, bars, springs, plates, solids. So now I have my elements defined and where they connect. So the degrees of freedom are identified because I have nodes. And if I know the type of elements, I would know the degrees of freedom. So step number two would be to write the element stiffness matrices. These are the lowercase k's, right? Step number three is to assemble the global stiffness matrix. This is the uppercase K. using all the lowercase k's or the element stiffness matrices. If I have K, I can write the global stiffness equation. F is equal to uppercase K multiplied by U. Step number 5 would be to apply the boundary conditions. Step number 6, solve for the unknown unknown displacements and external forces. And step number 7 would be to use the element stiffness equations lowercase f equals to lowercase k times u to solve for the element forces or the internal forces. Okay. So this is kind of an outline for the steps that we're going to go through when we apply the finite element method to simple problems like what we're going to be doing here in this class. We want to apply these steps today to solve an example here of two cylinders, AB and BC, that are connected together. AB has an area of 0.1 square inch. And BC have an area of 0.15 square inch. Both of them are made of the same material, so they have a modulus of elasticity of 10 times 10 to the power 6 psi. AB is 10 inches long, BC is 12 inches long. AB is fixed or connected to a wall at A. C sits next to a wall and the clearance is 0.002 inch. We have a force applied at B of 1 kip. We want to find the wall reactions. We want to find the deflection or the displacement of B. And we want to find the internal forces, of course, in AB and BC. And I think you've all seen similar problems in solids, not in statics. Have you done a problem like this in statics? Why not? This looks like simple, right? It's even simpler than truss and beams and frames that we've done in statics. But we haven't done it in statics. Why? It involves material properties. Good point. Why does it involve material properties? It is. It's not static. It is static. Of course, like, yes, there is deformation. But when we did statics, we understand that all the bodies are deformable. One simple reason. If there are two reactions at A and at C to resist this 1,000-pound force. So looking at this, we think like, oh, most likely, we don't know yet, but most likely there is going to be a reaction at A and this is going to hit the wall at C and there is going to be a reaction at C, right? Now, if that's the case, I can draw a simple schematic here and say, well, if I do have, this is like to represent AB, and this is BC. If I expect this wall at C to push back, and this wall at A to hold AB, because there is this 1K applied here, so I'm thinking of this as RA and this is as RC. From statics, we learned how to write equations of equilibrium. So how many equations of equilibrium can I write for this problem? Just one, namely, if this is my X direction, right? So I can write sum of the forces in the X direction is equal to 0. If I take the positive X as positive, then I will have like this minus RA plus 1,000 minus RC is equal to 0, which I can rewrite that as RA plus RC is equal to 1,000. Yeah, I have one equation, but two unknowns. I know both walls are going to contribute to resisting the 1,000 pounds, but I really cannot just say, oh, let's put 500 to this side, 500 to the other side, and I'm done. It's not going to be distributed evenly. Why not? Areas is different. The length is different. In other words, the stiffness is different. So how is this going to be governed? First of all, mathematically, I need an additional equation. Where is this additional equation going to come from? Displacement of B. What is it that we are trying to make sure is respected? We call it a compatibility equation. And it's a good pointer here, displacement at B. The two parts are going to stay connected. So if B is shared, when AB is going to be elongated, BC is going to move until it hits the wall, then it's going to get compressed. So there is another constraint that we have to respect, or a compatibility equation that I can come up with. What is this compatibility equation going to tell me? What is it that I want to enforce? When I put this 1,000 pound force, what's going to happen? AB is going to elongate, and BC is going to be pushed until it hits the wall, if it hits the wall. Now, if it hits the wall is going to push back. When the pole push backs, what is going to do to BC? Compress it, right? It's going to compress it. At the end of the day, both the elongation of AB and the compression of BC combined are going to have to be equal to this clearance. They cannot be more, it cannot be less. So I can come up with this additional compatibility equation. So here we have two unknowns that are greater than one equation of equilibrium. Therefore, we call this an indeterminate problem. So we need an additional equation that we call compatibility equation. And we said that delta AB plus delta BC, both of them combined, must be equal to this 0.002. All right, what is delta AB? Can we measure the deformation in AB? We can if we know the internal force in AB. What is the internal force in AB? I'm gonna have to cut through AB. So I'm gonna have to cut here. And then when I cut, I can draw a free body diagram of the left piece. So I draw a free body diagram of the left piece. So where I'm cutting, I'm exposing the internal force. Now here at point A, I have this RA, and where I cut, I expose the internal force that is NAB. From this, I can conclude that this unknown NAB must be equal to, if I apply equilibrium, RA, and NAB is pulling the member, so it must be tension. Similarly, if I cut here and draw a free body diagram of this right portion, if this is C, I have an RC pushing, and where I am cutting, in order for this piece to be an equilibrium, there must be an internal force pushing back, and this is NBC, and this NBC, because it's within the member BC, right? This NBC must be equal to RC. Now, why is this important? Because when I look at deformation of axially loaded member, it is equal to, if you recall from solids, PL over EA. But more precisely, this P is rather the internal axial force in the member. So I can write this delta AB as NAB times L of AB divided by E, which is the same, divided by the area of AB. plus for delta BC, I have NBC multiplied by LBC divided by E divided by the area of BC. And this is equal to 0.002. Now, before I go any further, let's make sure that C is going to hit the wall. How do I make sure that C is going to hit the wall? Why? AB. You mean the elongation of AB? Right. So can I calculate the elongation of AB pretending that the wall does not exist? What is that going to be? So if there is no wall, delta B is going to be equal to the 1,000 pound going entirely into, because RA is going to be equal to 1,000. If there is no RC, okay, so if there is no wall, RC equals to 0 and RA equal to 1,000, right? So this is no wall. So delta B then is going to be equal to this 1,000 multiplied by LAB, which is 10, divided by E, which is 10 times 10 to the power 6, divided by the area of AB, which is 0.1 inch, square inch. When I do the numbers here, lots of ones and zeros, right? So 10 to the power 4 divided by 10 to the power 5, I get a 0.1 inch. Now, what does that tell me? If delta B is going to be moving 0.1 inch, then delta C is going to move 0.1 inch, which is greater than 0.002. So for sure, C is going to hit the wall. If C is hitting the wall, then this compatibility equation here is correct. So let me substitute for, if I look here, I can substitute for NAB by RA. So I can come here and say RA. And for LAB, I can put 10 divided by 10 times 10 to the power 6 divided by 0.1 plus. And RA is positive because it's tension. Okay. NBC is equal to RC, but please pay attention because this is compression. Like I said, RE here was tension. So I can replace NBC with a minus RC. And LBC is 12 divided by 10 times 10 to the power 6 divided by 0.15. This is equal to 0.002. Now I have a second equation in RA and RC, and I have a first equation RA and RC. From 1 and 2, we can solve for RA, and we'll find that RA is equal to 555.56 pounds. And I can solve for RB to find that RB is 444.44 pounds. If I know RA and RB, these are the wall reactions that we were asked to find. And if I know RA and RB, I know the internal forces. So I can say here that NAB is equal to RA equals to 555.56 pounds tension. And NBC is equal to RC compression, which is equal to 444.44 pounds in compression. The other thing we were asked to solve for was how much B is going to displace. I already have an equation here for delta B that we use here with 1,000. But now we know if C is hitting the wall, that delta B is going to have to use the correct NAB, which is 555.56 multiplied by 10. So the only thing that's changing is the 555 instead of the 1,000. 10 times 10 to the power 6.1. And when I do the numbers, I get 0.0055556 inches. So this is how we solved this problem when we took solids. We write equations of equilibrium, we write a compatibility equation. We have to understand how everything is behaving, which is really helpful. Now today, we want to learn or want to apply the finite element process to solve the very same problem. So we want to apply the process that we just outlined here to solve the exact same problem. So what I'm going to do here is I'm going to follow the steps that we developed together. So the first step here is meshing. So I'm going to look at this and say, well, it looks like I have two axially loaded members that behave like bar elements. So I'm going to make, this is physically apparent. I'm going to use simply two elements. So I'm going to use, so here I'm going to solve it using FEM. And I'm going to start by first meshing. So node A is really going to become, or point A is going to become node 1. And B is going to become node 2, and C is going to become node 3. Now, at node 1, I have a wall, meaning I have a reaction RA. So that's my external force that I do not know. I also have a displacement U1 that is equal to 0. At node 2, I have a displacement U2 that we do not know. But we have an applied force of 1,000 pounds. At node 3, we know that we have a displacement U3 of 0.002. And we have a wall reaction that we do not know of RC. So really here are our three unknowns, RA, U2, and RC.
Just go through and make sure that it wouldn't come off.
Of course. Because in making sure it hits the wall, this is how I identify this boundary condition. I cannot say U2 is equal to 0.002 unless I know it's hitting the wall. Otherwise, I'll be solving a different problem. Okay. So here I have two elements. Element 1 has a stiffness K1 and element 2 has a stiffness K2. So one of the first things I want to do here is to evaluate K1 and K2, because my next step is to write my element stiffness matrices. Now I'm using a bar element. So this, I know that this K is the same as that of a spring, but I want to find what is K1 and what is K2. So K1 is equal to EA over L, right? And here would be the area of AB, and this is the length of AB. So E is 10 times 10 to the power 6. The area is 0.1, and the length is 10 inches. I do the numbers here, and this is 10 to the power 5 pounds per inch. For K2, I have E times the area of BC divided by the length of BC. This is equal to 10 times 10 to the power 6 multiplied by 0.15 divided by 12. I do the numbers and I get 1.25 times 10 to the power 5 pound per inch. Okay, so far we just found the stiffness, but in order to write the element stiffness matrix, I can come here and say K1, which is a 2 by 2, is equal to K1 10 to the power 5 minus 10 to the power 5 minus 10 to the power 5 and 10 to the power 5. This is still pounds per inch. I can also write the stiffness matrix, K2, which is also a 2 by 2. And this is going to be 1.25 times 10 to the power 5 minus 1.25 times 10 to the power 5 minus 1.25 times 10 to the power 5 and 1.25 times 10 to the power 5. This is in pounds per inch. Just to remind you, this element stiffness matrix for node 1, for element 1, extends between node 1 and node 2. So corresponds to degrees of freedom 1 and 2, 1 and 2. And this element stiffness matrix for element 2 extends between node 2 and 3. So it corresponds to degree of freedom 2 and 3, 2 and 3. So step number 3. assemble the global stiffness matrix uppercase K. And this K, because if you look at the total system, I have 3 nodes and 3 degrees of freedom. So this K must be 3 by 3. So I have here this uppercase K is equal to, and it's a 3 by 3, right? Now, looking here at K1 and K2, I see 10 to the power 5 everywhere. So I'm going to take 10 to the power 5 outside to make it simpler. And then I'm going to write it down here. And we are going to assemble it using degrees of freedom. So I have 3 rows and 3 columns. 1, 2, and 3. 1, 2, and 3. K1 between 1 and 2 is going to go here. And K2 between 2 and 3 is going to come here. Right? And you can see clearly that 1, 3 is a 0 and 3, 1 is a 0. So let's put here the entries. And I'm trying to use different colors. I hope it's clear on the screen. So K1, I'm going to have a 1 and a -1, because 10 to the power 5, and -1 and a 1. I hope you see where I'm getting my numbers from. Okay. For K2, I have here a 1.25 times 10 to the power 5. And this is 2, 2. So this is coming also here. So I'm going to say, in addition to this one, and I'm going to go in black, I'm going to do a plus, and I'm going to put a 1.25. Then here I have a minus 1.25. Here I have a minus 1.25. And here I have a plus 1.25. This is my global stiffness matrix. And this is also in pounds per inch. We're good so far?
So what size matrix is that? Is it a 4 by 4?
Look at it carefully.
It's a lot of lines.
Next, we are going to write our global stiffness equations. So now I'm going to write in step number 4, write the global stiffness equation. And just to remind you, this is the one that looked like uppercase F is equal to this matrix K times U. So I need my uppercase F. And this is the vector of global or external forces. So looking at my diagram here, I have RA, I have 1000, and I have RC. Correct? So I'm going to write RA and RC, both are unknowns. And here I have 1000 pounds. This is equal to the 10 to the power 5 multiplied by, and I'm going to copy my global stiffness matrix. I have a 1, a -1, and a 0, a -1, and I add these two together. So the only entry that's getting components from K1 and K2 is the one that goes in row 2, column 2. So here I have a 2.25 minus 1.25, 0 minus 1.25 and 1.25. This is multiplied by my nodal displacements. Okay, looking back at my original mesh. And looking at nodal displacement. The displacement at node 1 is a 0. The displacement at node 2 is not known, so I'm going to put it in red. It's U2, which corresponds to UB, by the way, or delta B, right? And because we know it's going to hit the wall, the displacement at node 3 is a 0.002. I really did two steps here because I showed or applied my boundary conditions. So this 0 is U1 and this 0.002 is U3. So by setting them, by giving them number, I really want to step number 5, which is apply the boundary conditions. In this case here, U1 equal to 0 and U3 equal to 0.002. Now, when I apply the boundary condition, you look here carefully, I have 3 equations and 3 unknowns. You are correct. RA and RC, the way I am applying them here, I really should put a negative sign. Thank you. If I didn't put a negative sign, it's as if I'm assuming them going in the positive X direction and I will get them as negative X. All right. So now when I apply the boundary conditions, how do I solve? Because U1 is 0, I can cross the first column of K, because this is all going to be multiplied by 0, right? And I can also choose to cross the first row for now, because we're trying to solve for the displacements. This is just how to solve these 3 simultaneous equations. So if I do that, I end up with 1000 is equal to 2.25 times 10 to the 5 U2 minus 1.25 times 10 to the power 5 multiplied by 0.002. And I also get minus RC is equal to 1.25 times 10 to the power 5 U2 plus, there is a minus sign here, sorry, plus 1.25 times 10 to the power 5 multiplied by 0.002. If I call this equation 1 and equation 2, we can solve 1 and 2 to find that U2 is equal to 0.000555 inches. Really, they're going to be 6 eventually. And RC is equal to 444.4 pounds. Then I can come back and use my global stiffness equations. So this is step number 6. Actually, starting from here is step 6. So 5 is apply the boundary conditions, and 6 is to solve. So we started from here solving. And then we're going to use the first global stiffness equation to find RA. So looking here at my equation, I can say that RA is equal to minus 1 times 10 to the power 5 multiplied by U2, which is 0.00555. Because now I solve for U2. So I'll find here that this is equal to 555 minus, sorry. And by the way, hold on a second. Oh, there is a minus sign here. That's correct. So minus RA is equal to minus 555.5 pounds. Therefore, RA is equal to 555.5 pounds. If you compare these numbers to what we got from using the classical method, you'll find that they're the same. And then the last step, so we are up to step number 6. Step number 7 is to use the element stiffness equations to solve for the element forces. Why do we need the element forces? Because the element forces are the internal forces, right? So step number 7, use the element stiffness equations to solve for the internal force. In this case would be NAB and NBC. Now NAB is it comes from the element forces in AB. So if you recall, if this is AB, extends between 1 and 2, or really A and B. The element forces would be F11 and F21. And the element stiffness equation here would be F11 and F21 is equal to, I go back to my element stiffness matrix, which is this. So that would be 10 to the power 5 times 1 minus 1 minus 1 and 1 multiplied by U1 and U2. And what is U1 and U2? U1 is a 0. And U2 we just found to be equal to 0.00555. From this element stiffness equation, I find that F11 is equal to, you see, 10 to the power 5 times minus 1 times 0.005555. So I get here I think I have an extra 0. Okay? There is an extra 0 here. 0.005. So sorry for that. So please correct U2. U2 is 0.00555. Okay, and also here. Okay. So now when I correct it here like this, I have 10 to the power 5 times 0.00555 with a negative sign. So I end up getting a minus 555.55. And F21 is equal to, now I have a positive 555.55. So one is negative, one is positive. Is AB in tension or in compression? How did you know? This is pulling, and this is also pulling. So one had to be positive, one had to be negative, but we can clearly see from that that AB is in tension, 500, and NAB is equal to 555.5 pounds. So here I use my first element stiffness equation. Then for BC, we're also going to show BC or 2-3. And my element forces are going to be F2 as it applies to element 2 and F3 to element 2. I can write my element stiffness equation as F22, F32 equals to 10 to the power 5, 1.25 minus 1.25 minus 1.25, 1.25 multiplied by nodal displacements. At 2, we have this 0.00555, and at node 3, I have 0.002. I do the numbers, and I get that F22 is equal to a positive 444.44, and F32 is equal to minus 444.44. These are in pounds. Now look at this, positive, negative. So BC is in compression. BC is in compression, and NBC is equal to 444.44 pounds compression. So this is the internal force in BC. This is the internal force in KBE. And we did solve for RA or reaction at C, as well as the displacement at B. So this was a nice demonstration of how we apply the 7 steps of the finite element process that we have written down here to the same example you did in solids, and we were able to compare the 2 methods. The beauty of the finite element method is that I do not have to worry about drawing free body diagram. coming up with compatibility equation. I just have to discretize. It's very well suited for a computer program to break it down, to write the element stiffness matrices, global, assemble the global stiffness matrix, apply the boundary condition, solve for the unknowns, use the element stiffness equations to find the internal forces. You got it all. I hope you like it and enjoy it. I ask you to please, while this is still fresh and you still remember, to go back home and work on homework number 4, which is a direct application of what we did today, as you also prepare for our first exam this coming Tuesday. The exam is going to be similar to the homework problem. So there are going to be 2 or 3 problems where you are going to demonstrate, you understand the concepts of analysis and design of a machine component. And more specifically here, we are focused on shafts, but I would like to see a good understanding of the process, both the analysis and the design. So the exam is going to cover both. Similar to what you did in the homeworks, you did a shaft without stress concentration, you did a shaft analysis with stress concentration, and you finally did shaft design, where you went from a first iteration to a second iteration to making sure that you are meeting the design factor requirements. Okay.
Or like I would have a quiz where you have names open and enter results, or you just start the paper.
Yeah, because this is going to be handwritten, unlike a multiple choice. I think it would be easier if we just all do it on paper and submit the paper at the end, so you don't have to worry about scanning and all the good stuff. But I ask you to please make sure you have properly labeled diagrams before you write equations. Make sure I can follow and understand your approach, your logical thinking of how you're approaching the problem. So in case you do a mistake, you allow me to give you as much as possible partial credit. Okay. Is that clear to everyone? And again, the exam is open book, and you are welcome also to have an equation sheet, if that would help. I think we don't have equations more than one side. So I think 8.5 by 11 one side should be more than sufficient. And again, you have your book, right? So this is just a bonus. Everyone is clear? All right. I hope you're enjoying the material, and I look forward for you demonstrating that on the exam. Thank you.